Okay, so in this video we're going to talk a little bit about some of the properties of water and how hydrogen bonding affects how water behaves and how that is super important in various aspects of biology and life on Earth. So the first thing we need to talk about is density of water, as this slide is saying. So it's important to know, to start with, we're going to be talking about water temperature here, and the temperature of a substance, whether something is hot or cold or hotter or cooler, is really a measurement of how fast the particles, usually the molecules, in that substance are moving around. Now, it's going to be a hard thing to wrap your head around if you haven't taken much chemistry yet, but that's all temperature is. It's not how hot or cold something is, really. It's really how fast are the particles that make that substance up moving. Are they moving like this? Are they moving like this? Or are they moving like this? All right, so if you can think of it this way, if you were to, right now it's the height of summer, if you were to walk outside your front door right now, the air would feel incredibly hot. And that's because the air molecules are moving really, 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 really fast, and they're slamming into your skin really hard, and that's the heat. That's how you feel it, as being very hot air. If you were to walk outside the front door in December or January, the air molecules aren't moving as fast, and so they're not hitting your skin as hard, and it doesn't feel as warm. So basically, temperature is a measurement of the speed of molecular motion, or how fast are particles in that substance moving around. All right, so now let's take that to water. Now, water molecules, we've spent some time looking at those. They're very small molecules. They only have 3 atoms, 2 hydrogens and an oxygen. So they're not very big. And for how small they are, they actually make a lot of hydrogen bonds. So every individual water molecule has the ability to make up to 4 hydrogen bonds, or 4 weak attractions, with its nearest neighboring water molecules. But those attractions are weak, and those are often broken and reformed. So if I am an individual water molecule, I could be making 4 hydrogen bonds this way, and then that way, and then over here and up there. So I'm making 4 hydrogen bonds always, but they're not always in the same direction or to the same molecule, and they're constantly breaking and reforming. But 4 bonds per each individual, or 4 attractions per each individual tiny water molecule is a lot. All right, so this is why these are significant when you have a lot of them working together. So let's put all this together. On the, if I can get this to work, right, on this diagram right here, we are seeing a picture of liquid water, like what would be in a water bottle. The water molecules, you can see their hydrogen bonds. They're being attracted to each other, but they're moving around pretty quickly, because this is not ice. It's not really cold. It's room temperature water, let's say. So these molecules are moving like this. They've got some energy, and because they're moving around, they're able to sort of pull away from their nearest neighbor, and then they get attracted to a different neighboring molecule. And because they're so busy and moving around, you can see how they end up sort of all getting quite crowded. All right, because they're constantly flying by each other, and this one's moving up here, and this one's moving over here, and this one's moving down here, and they end up getting kind of close together. So that's what the molecules look like in this bottle of liquid water, pretty close together. If we take this and we freeze it, so we're freezing the water, really this is not a chemical reaction. It's still water molecules. Look, they look the same. A red ball and 2 white balls, a red ball and 2 white balls. So we have not done a chemical reaction. We haven't changed water. It's still water, but here it's much colder water, which means the molecules are not moving as fast. They're still water molecules, but instead of moving around like this, like they are in the water bottle, now they're in the ice cube, and they're kind of just moving a little bit like this. And when they're only moving a little bit, they don't have enough oomph, they don't have enough speed to break apart from their nearest neighbor. So if we were to take this water molecule here and this water molecule here, they get attracted to each other. That's what the dotted line is showing us between the two. and water molecule A and water molecule B, they're only moving a little bit and they're not going fast enough to separate. They're just kind of jiggling side by side. And since these water molecules have the ability to make 4 hydrogen bonds with their 4 nearest neighbors, the only way they can do that and make all 4 attractions is by kind of spacing each other out and kind of arraying themselves like this pattern you see here. You see there's like a sort of hexagon pattern going on here between these water molecules. And then there's also hydrogen bonds going back into the slide and coming out towards you from the slide. It's a 3-dimensional thing, even though that picture is just flat. So to allow each water molecule to make the 4 attractions to its 4 nearest neighbors, they have to spread themselves apart, and they create this kind of sort of patterning within the ice cube. You can't see it obviously with your naked eye, but the molecules inside this ice cube look like this. So this explains several things about ice. Number 1, it explains why snowflakes have 6 sides. If you've seen microscopic pictures of snowflakes, we now can explain why they have 6 sides, because the molecules making up that snowflake are attracting each other in these arrays of 6 so that they can space themselves out and make all these hydrogen bonds. It also explains why frozen water or ice will float on top of liquid water. So, if you put ice in a drink, soda, you put ice, the ice comes to the top. It doesn't sink to the bottom. Most things, when they get colder, the molecules move less and less and less. And so the thing kind of shrinks up and gets smaller and more compact. Most things get more dense and more compact as they cool down because the molecules aren't flying around as much. The opposite is true of water. As it gets colder and freezes, the molecules space themselves out more so that they can make all these attractions. So as water freezes, it actually gets bigger or expands, which you've probably experienced if you ever left a beer in the freezer for too long and it froze. It will expand and pop off the top or break the bottle, or if you put things in the freezer liquid, they get bigger. That's the water molecules spreading themselves apart so they can make this structure. Why is this important to biology? Well, it helps us when it gets very cold and water in lakes and oceans freeze. Instead of the water freezing and then the cold water sinking and then everything freezing from the bottom up and you end up with a solid chunk of ice, which is what would happen if the cold water sunk and got more dense. Because the cold water or the ice gets less dense and floats on the surface, then you have this layer on the surface of the lake or the ocean, but that protects the water underneath from freezing. And so you have this kind of insulated layer of ice on the top if it's a pretty deep lake, and liquid water underneath. And so in these areas of water like large lakes and oceans, even in the depths of winter, there's always liquid water. It's hidden below the surface, but it means that life can exist because life needs liquid water to survive. And if all the water turned solid in the winter, turned to ice, everything would die, which would mean every winter, in certain areas when everything froze, or in ice ages that the planet has been through, when the majority of the water froze up, life would die. And we'd be back to the drawing board in terms of evolution every ice age. But luckily that didn't happen. Luckily, ice floats, liquid water is protected underneath, and life can continue in that protected liquid water even through cold periods. So thank heavens that ice floats on water. It's enabled life to persist even as the planet has gotten colder and gone through cold phases. So it's one really important feature of hydrogen bonds. It allows ice to be less dense than liquid water, therefore it floats.